Good morning. Nowadays, reproducible and traceable research is becoming more and more important. Let me give you a small example. Our institute produces trends on several species every year. A few years ago, one of our stakeholders said, this data is rubbish, this trends doesn't make sense. How do you end up with that number? Well, we replied, our analysis is based on code. The code is under version control. The data is under version control. Both are available for inspection. Our ability to say that immediately changed the tone of that conversation. And this strengthened our beliefs that we really should put all our data under version control. That's why we wrote the Git to our data package to make this easier. So what are the requirements to do this? First and foremost, we believe that you should store your data in an open and a plain text format, because that is the easiest way to access the data for other people using whatever software they would like to do. Then the data you read should be exactly the same information as the one you stored. This seems trivial, but think about something like write.table. If you use that to store plain text files, you lose the distinction between characters and factors. You lose all information on the order of the levels. You lose levels which are not present in the data. Although we are talking about plain text formats, we should try to use that as compact as possible. And history should have a meaningful interpretation. And of course, we'd like to integrate it with the analysis. So what are data format we choose? First, we choose to split the information on two separate files. One tab-separated file containing the data itself, and another in a YAML format containing the metadata on the file. It contains all file names, all variable names, their class, and their format. For instance, in case of a factor, what are the levels, what are the order of the levels, what are the indices of the levels. So then we know we have all the data to get the same results back. But we're talking about compact data, and instead of making it compact, we're even adding another file. But then again, we really thought about what should we store in the data. For instance, we only store data which contains information. And something which doesn't contain information is, for instance, row names. If a row name contains information and you want to store it, then add it as a variable. Don't use it as row names. Another thing that we do is, for instance, we only place quotes around character variables when they're really needed. For instance, when you need some quotes is when the delimiter is present in the character variable. That's one of the reasons why we chose for a tab separator, because tabs are less likely to be present in your characters than, for instance, spaces or commas or semicolons. Notice that we have two versions, the verbose version or the optimized versions. The optimized version goes even a bit further and uses the metadata to the max to even get more compact data sets. And this is clearly seen when you think about factors. The verbose option stores factors as their label, which makes it human readable, whereas the optimized version stores their index number, which is much more compact, especially if you have quite long characters and a few levels. But even if you have like 1,000 levels, it's probably still be more compact than storing them verbose. So how can you use it? First and foremost, you don't have to use this with Git, but it's tailored to work together with Git. You don't even have to use it with version control. If you prefer other things like Mercurial or SVN, you can use them as well. So that's why we just allow you to write to the disk. Use the write VC function. VC stands for version control. You provide the data frame, a file name with a path that is relative to the root, which is the project repository. The function will prepare the data and write the tab-separated file and the YAML metadata file to the disks, and will return the names of those two files and their hashes. This is interesting in case you want to document your import step. And reading it back again is quite simply just use the read VC function using the name and the root of the repository. And then you get a data frame back which has exactly the same information as the one you stored. So we also do some optimization for version control. Imagine that we have a very simple data set, version 1. We stored it to disk, we committed this change, and then we updated the second version. What did we change? The third row was updated, and the first and the second row swapped positions. So if we would commit that again and as is, then this would be the diff if we used unsorted data. The update of the third row is stored as removing the old version of the third row and inserting the new version of the third row. The position change of the second row is indicated as removing it at its original location and inserting it at the new location. In our opinion, the position of an observation should not contain information. So in this case, if we would have a stable sorting of the data, and we would store the data again, then the same diff would be much shorter and only contains meaningful changes. In this case, the update of the third row. So GitR data does that kind of sorting for you. Imagine that you would swap two columns, then the diff would be even bigger because every single row would have been changed. So we also sort the columns. So let's see what effect that this has. We have used the airbag data set as an example. We took a 90% random sample, randomized the rows, randomized the columns, stored that to disk, committed the data, and repeated this process for 100 commits. If you do that and you store the data using a default write.table, then the Git repository size grows really fast. If you would, for instance, use RDS files, it still grows quite fast because binary files are notoriously bad under version control. Another option here would be to manually sort the data to get a stable order of the observation and a stable order of the columns, and that would be much more efficient. Big downside of this is that you will have to remember to do the sorting and to use exactly the same sorting every time over and over again. That's something that WriteVC does for you. You only have to specify the sorting the first time. And on top of that, you get the optimization to create even more compact files. So what can we store? GitHub recommends to keep single files below 100 megabytes. In case of the airbag dataset, we can store about 1.5 million rows. And they also recommend to keep the history under 1 gigabyte. And if we would continue the 90% subsample thing, we could do about 17,000 commits. Of course, if you apply this to another data set, you'll get other numbers. So how fast is it? Of course, we need to do a lot of checking, a lot of data preparation, so it takes a bit more time. It's about twice as much time you need as a default write.table. However, reading is as fast as, or almost as fast as a default write.table, because we can use the information we have from the metadata to provide more information to when reading the data, because we already know what kind of data format, what kind of data type we are reading. So if you are a Git user and you like to use the Git to R package as well, then we have some extra methods for you. For instance, if the root is a Git to R repository object, then you get an extra argument, which is the stage, which allows you to automatically change a stage, and it changes when you write the data. Notice that you get, in this case, a warning that you didn't provide any sorting. So you have to provide the sorting variables yourself, because it's very hard to find out what would be a relevant sorting variable. So in this case, we rewrite the data and now use the sorting argument to provide the column names by which we have to sort. You only have to do this once. Notice that you now get an error, because each time write_vc detects that the change might potentially lead to very large diffs, it will throw an error and gives you an indication on the reason why we think that you did something which you may not want to do. In this case, you changed the sorting. But here, we made a mistake. We first forget to do the sorting, and now we wanted to do the sorting. So this is something that we really want to change. So we can override this by adding the strictest false argument. And then all the errors will turn into warnings, so you still know that there was something going on, but the data is changed. Since we were using a git to R repo, we can commit it from within R. So if you want to use it within an analysis workflow, then we have a useful function, which is a recent commit, and you can use that to find the latest commit in which a file or a git to R object was last updated. And you get exactly that commit. And what we recommend is that when you do an analysis, is first store all your data into the Git repo using write_vc, and then base your analysis on data frames you read back from the repository using write_vc, and document the name of the repository and the commit that is relevant to that data set, and store that alongside your analysis. And not only store that, but maybe you should also report that information, because that makes your analysis much more traceable as well. So finally, if you're interested, you can find the package on the ErrorOpenSci GitHub pages or on CRAN. We have some installation instructions on the website. There are a few vignettes about this talk more in detail, and all documentation is over there. And finally, I would like to have a thank to Brody Gaslam and Joyce Robbins, which reviewed the package on ErrorOpenSci, and that's really improved our package. And for those who still have rooms, some space on your PCs, we have some hex stickers as well. So come and join me if you like them. Thank you.
Thank you very much, Thierry. We have plenty of time for questions. There's one in the back. And please keep your hands open if you have questions, so we can arrange the mics.
Thanks for the talk. I just wonder if you have a package with data, can we use your package to follow the change in the data that are included in a package? And is it able also to deal with lists if you store several objects in a list? And is it possible to use this type of
so the first question was, can you use it to see what changed in the data? Well, what I typically do is I have an import script. For instance, if I use data from a database, and then I run the same import script to write to the data, and that really makes it quite easy for me if I look into the Git diffs to see what's changed actually in the data. Currently, we only work with data frames, but it's an S3 method. So if you have an idea on how to store lists, you could easily expand the package working with lists. But the problem with lists is that it's very free style of objects, and it's really hard to make methods for that. But if you have a fixed set of lists, yeah, you could do.
Hey, sorry. When it comes to storing attributes like the levels of a factor, how do you handle, what kind of attributes do you allow in that context? Because things like label can be quite useful. Is there like a list of things you're allowed? And also, do you handle like the fact that attributes can be abused? So on a factor, for instance, if I really wanted to, I could turn the levels into a gigantic data frame embedded on each vector as well.
Well, we actually just take the levels and the labels as is in the data frame, and they get all stored in the metadata. So if you would do any crazy stuff within, as long as R can handle it, we should be able to handle it. Things like attributes are ignored. So it's just currently just using a really plain and simple data frame.
We have time for one more question.
Why did you decide to develop your own package rather than using, for example, Git LFS for large file storage?
Well, we actually started to write data to just start use CSV files to Git repos to document our data. And then we said, okay, this is not working very well because all these problems that we have to do some extra data manipulation again, because the data is not always exact same thing as you get. And then we said, okay, maybe it's useful for some other people too, and that's why we turned it into a package and made it available.
Thank you very much, Thierry.
You're welcome.